In this last subsection from the compression chapter, I want to talk about the Burrow Wheeler transform. That's the most sophisticated text transform that we will cover. And again, it will not by itself make the text compressible, but it makes redundancies in the text explicit and then allows other compression methods to work much more effectively. And that makes the Burrow Wheeler transform the core ingredient for modern compression, both for static compression, where you compress and decompress, and for data structures where you work on the compressed representations. For both, the Burrow Wheeler transform has been instrumental. And it's also a beautiful theoretical idea. Maybe also as a historical side remark, when the transform was first thought of, it was deemed impractical because it needs a lot of extra memory. It needs to have the text all in main memory. And so it was deemed impractical and not pursued. And only much later it was published when people realized that it is practical with the improvements of hardware and memory sizes. So this also tells a story about algorithms in general. Sometimes a sophisticated idea looks impractical at the time you think of it, but it's still worth exploring because it might become practical in the near future. And this is what definitely happened to the Burrow Wheeler transform. What is it, the Burrow Wheeler transform, the BWT? It's a way to scramble around the text characters. It uses the same letters as the source text, but in a different order. And that order is specifically chosen to help compression, to help other compression methods. We'll come to that in a second. A downside from that is that it needs the entire text to compute. You need the entire text to compute the BWT. And maybe what convinces you most is if you take the BWT, follow it by move to front, then run length encoding, and then Huffman at the end. That is at the core what is behind the bzip program. And that achieves the best compression we know for English text. I've shown you here, this is just the English Bible. So that's some 4 megabytes. That's all there is to it if you store it in plain text. If you use gzip, the GNU zip, you get it down by a factor of 4, which is not bad. 7-zip, which is often deemed the most effective general compression method, is much better than GNU zip, gets it down to that. But bzip actually beats 7-zip for text. And without discussing this much further, it shows that having the right conceptual ideas achieves good results also in practice. And that's even though these two are very highly engineered, this comparatively simple method beats them by using the appropriate tools. To be fair, I should mention here that bzip tends to be slower than the other methods. So there's a trade-off to be made between the time it needs to compress and decompress and the compression ratio. But if the actual compression ratio is what you're after, then bzip is very solid. Okay, I finally want to tell you what the BWT is. For telling you that, I need to introduce a cyclic shift of a string. That's a simple concept. If you have a text T, a cyclic shift just means you start in a different position and wrap around. So if you write the string like this on a circle, time flies quickly, then originally this was the starting position. I can move the starting position to some other point, and then I start reading the text from here. That's a cyclic shift. Cyclic because it's on the circle. I think it's intuitive enough. And so one cyclic shift of this string is flies quickly time. Not sure if that's a sensible sentence, but it's the best example I could come up with. If we add an end of word character, and you're by now familiar with these, then the cyclic shifts become invertible. I can always continue shifting until the $sign is at the last position. So that's a convenient convention, and we will use this for BWT as well. So take a text, append the dollar character, and then the Burrow Wheeler transform works as follows. You take all cyclic shifts of your text with the $sign at the end. You sort all those cyclic shifts lexicographically, and then you take in that sorted list the last column top to down and read down these characters. And that gives you the Burrow Wheeler transform of the text. This, I'm sure, sounds crazy. And it kind of is, but it's magic. No, it's a smart trick and a smart way to exploit redundancies, but I'll show you in a second. Let's first see an example on how this works. So here's a sample text that we will see a couple of times over the next slides. Alf eats alfalfa. That's some sort of grain or so, some plant. So it's an actual valid English text, in case you care. For the BWT, this is not the main point. What we need is all the cyclic shifts. So this is the text with the dollar at the end. You get all cyclic shifts by starting at a certain position and then starting from the beginning modulo the length of the text again. So these are all the cyclic shifts, right? Starting at all positions, and you see visually how you just shift things by one character to the left when you move down one line. Now we lexicographically sort these, and that gets us this list. So these are the same strings, but now sorted alphabetically. So the dollar comes first. That's our convention from Unit 6 as well. Then space comes before all the alphabet characters. So if you look at this list, this is always sorted, right? Goes from small to big. But the only thing we really take from this picture is the last column of this sorted list. So you read this column top down, and that is the Burrow Wheeler transform of this text. And if you look at this gibberish, it's not at all recognizable where this came from. It looks quite different and quite weird. You might notice that there's these runs of characters, and that is a typical thing. It's definitely something that happens when the text is repetitive, and that will be what we're after. But the way we got to this BWT might still sound fairly wild. Now, I want to get you a little bit thinking, and in case this wasn't already on your mind, I want you to think about the relation between BWT and suffix arrays. So the concrete question is, we had the suffix array L, the leaf array, right? Well, the sorted suffixes of a text, take all the suffixes of a text and sort them. That's L, and we have the text, and we have the BWT and the text. And so the question is, if you have either combination of either L or B and the text, is it easy for you to determine what the other is? And yeah, I'd like to see a few more answers, and maybe up to 20. Then I'd like to show the results and move on. $17, $19. Okay, one more. We can get one more, please. And I think it's looking good. Yeah, so there we are. And let me lock that in. The majority got it right. As you probably noticed from this picture, I'll show you a better picture here. If you take cyclic shifts and sort them, you never really compare beyond the dollar character, because the cyclic shifts, these are all the different cyclic shifts. Dollar occurs only in one position. You never have a cyclic shift where the dollar occurs at the same position. You never have an equal there. So any comparison between cyclic shifts will have the same outcome as if you ignored the gray part and just looked at the suffix starting at the same position. Okay, so sorting cyclic shifts is the very same task as sorting suffixes. And that, of course, means if you have the suffix array and the text, then you know the sorted order. The only thing you need then is to jump to this last column, but that's always the character that precedes this index. So if you have, for example, here, if we know that this is the starting position, this A is the, what is it? It's actually the first character in the text. That's let's not use this example, that's degenerate. But this one, this is the suffix that starts at the second to last character. So what's the last character in this column here? That's whatever is preceding this. So if you just take I-1 and access the text character at that position, you get the BWT. So it's easy to compute the BWT from the suffix array and the text. A is, it's possible, well, it's always possible because you have the text. But A is more challenging because the BWT loses the information about where the text started. It only keeps this last character, the last column character, and that alone doesn't make it very obvious how to compute it. There are more sophisticated methods with a little bit of insight that make this possible, but it's not easily possible. Good, so that connection gives us an efficient way to compute the Burrow Wheeler transform, because sorting cyclic shifts is the same as sorting suffixes, and we know how to sort suffixes. All right, and here's the formula more explicitly that shows you how to get the character, how to compute B from L in the text. Here the text is called S, but other than that, it's the same thing. Okay, that's how we can find the BWT. That's the first good thing. We can efficiently compute it. The next question is, why is this any interesting? Why does the BWT help us in compression? And for that, I think I need here the example. What the BWT does is it groups characters by context, namely by what follows them. So for example, we have a context here. LF is repeated here in these positions. And you see it's grouping these A's together into a run. And the reason is that we have this ALF 3 times, and it's contiguous here. So all the occurrences of LF in the text are actually preceded by an A. If there were other things that precede LF, they would also be in this little contiguous range. So we group characters by what follows, and that means if there's redundancy in terms of, I don't know, TH is often followed by E, the BWT is able to pick that up. Well, if there's other characters that can come after TH, like A, then the BWT is still able to make that more effective by leading to local clusters of characters. So it groups characters together by what can come after them. And if if, let's do another example here. If that is my example, then in English you can have a T in front of it or an S in front of it, but you probably don't find an X in front of it very often. So in the region where you have HA in this sorted range in the front rows, the last row would contain S's and T's a lot, but no X's, and that's what I mean by local clusters here. And finally, if you have repeated substrings in S, you usually also get runs of characters in the Burrow Wheeler transform, as in this example. So that's what I already said here. Alf is repeated 3 times in Alf eats Alf alpha, and that repetition in the BWT leads to runs of characters. So this was only a vague intuition why the BWT will be helpful for compression, but it should give you at least some indication. I want to show this on a bigger example as well. So here we have this text, have, had, hadn't, hasn't, haven't, has, what. And if you look at the BWT, you find there's a lot of characters that are repeated. And if you then apply the move to front transform on the BWT, that's remember what bzip does, then you find a lot of zeros in the move to front transform of the BWT. Yeah, let me ask this question, and then that's the last thing for today. So a little just thinking from first principles on this example. We have this example text, have, had, hadn't, hasn't, haven't, has, what, and it's BWT, and it contains this long run of H's, like this one. Not quite as long, but this. What does that really tell us? How can we argue that this is occurring as a run of how can we explain this run of H's? And be very careful about how to argue about this, because several of these answers make sense, but they're not necessarily all correct. And again, so I left this here because it's insightful to look at this run of H's here. It's the same here. And because we're already at 12:30 and I have a follow-up meeting right after this, I think I'll have to close the vote now so that I can at least briefly discuss the result as well. So I marked essentially only this single answer as correct. Let me lock it now. And let's move back to this. So I said the correct answer is that all A's are preceded by an H. And that's the statement that we have all the A's in the text here. They're necessarily together because we sort the suffixes or sort the cyclic shifts. And if you check what comes before those, all H's here are before this A. So there's no other character in this example text that precedes the letter A. And that is guaranteed to give us a run of H's of the number of the length as many A's as we have, we will have a run of H's. Of course, it's also true that this text has long repeated parts. In particular, it has these repeated parts, space HA, space HA, space HA, space HA, quite a couple of these. And you can trace where they end up in the BWT. They also give rise to runs in the BWT, or at least local clusters, but not always contiguous runs. For example, here, if you look at this, this is all, maybe zooming, oops, that was a bad idea. All these are all the suffixes starting with HA, but not all of them are preceded by a space. There's also these two other cases. So even though you have this repetition, you don't get a clean run, you just get a local cluster of the space in the BWT.